I hope you enjoy the posters, the lunch, the weather, which has been fantastic today. So, and since typically after lunch people have a little bit of a lull, we brought something very special for you in these two speakers in this session. So we're very happy to welcome Professor Kyunghyun Cho. He's a professor here at NYU in computer science and data science, also a senior researcher in Prescient Design, part of Genentech, research and early development. Kyunghyun is also a CFAR Fellow of Learning in Machines and Brains and an associate member of the National Academy of Engineering in Korea. He does a lot of service. He's all over the place in ICML, NeurIPS, iClear, you know, all over. And
recording in progress.
Oh, thank you. And very well known for his work on recurrent neural networks, particularly GRUs, and as well all machine translation work, like really groundbreaking over the last few years. So we seem to be fine now. That's why I don't have to leave. Perfect. So please join me in welcoming Professor Kyunghyun Cho.
Well, thanks for the kind introduction. And then I gotta warn you that there's absolutely nothing about audio, music, or speech here. So it's going to be purely a textual, let's say, presentation I have. And I did actually warn Juan already when he invited me over to give a talk here that well, the last time I actually did anything with the audio was 2015, 2016, and 2018. And then it's 2023. So I told him that, okay, it's not going to be anything about audio. But hopefully, there's going to be a slight, let's say, twist to what you have been hearing and then what you're going to hear about later today. So what I'm going to actually tell you a bit about is a rehash of exactly what Leon Bottou, who is a scientist at Facebook AI Research, or the Meta, let's say, AI Research these days, who gave a talk at the keynote talk in 2015 at the ECMO, if I recall correctly, or ICMO. And then what he actually pointed out back then was that the machine learning has had a really great run thanks to this particular experimental paradigm that has been super successful. That is to collect the data and then split it into 80% training examples and then 20% test examples. And then we're going to make sure that whatever we do with our algorithm is on 80%, and then we check how well it works on the remaining 20% or the 10%, however many you have held off. That's all good. That's actually really good. That's exactly how the machine learning has made any kind of progress ever since, let's say, 80s and 90s. If you have heard of the MNIST, I'm pretty sure many of you have, that's a handwritten digit data set that actually started from the NIST data set that was released in the late 80s. And then literally that data set alone has pushed the whole field of the deep learning up until, let's say, 2010, when it was superseded by ImageNet effectively. And then the whole idea was simple. Let's take 80% of the data set as a training example, 10% validation, and then 10% test set. And then we're going to find an algorithm that's going to increasingly do better on the test set. That's great. But then what Leon already noticed in 2015 was that this experimental paradigm is reaching its limit. That is that unfortunately, this paradigm itself was relying heavily on a particular assumption that in fact started the entire field of the statistical learning theory, and that assumption is starting to be invalid in the real world applications that we started to, let's say, apply or to deploy our systems for. And in particular, what he pointed out was that, this paradigm still is driving us, but it's not going to get us all the way to this AI or our increased ambition. And then what we need to do is really try to work around this. So Leon Bottou said it in 2015. Obviously, the field did not listen to him. That's how the field of machine learning always works. Leon Bottou says something, and then we only listen to him about 10 years later. So Leon Bottou wrote a paper, actually a very thick technical report showing the theoretical foundations behind the stochastic gradient descent and why we have to use a stochastic gradient descent in 1998. And then only in about 2012, we realized that, indeed, stochastic gradient descent is the thing that we have to use. And then nowadays, everyone is using stochastic gradient descent. So I thought, okay, this is the right time. It's been 8 years since Leon talked about this. And then we probably need to come back to this idea and then trying to see, indeed, whether there is something that we can do beyond just checking the tested accuracy. So when we say this single experimental paradigm of checking the tested accuracy, this is what we mean. Somebody's going to go out there, collect the data, And then let's assume that you are working in a supervised regime, but it can very well be unsupervised. And then using that data, we're going to split it into the training set and the held out set. And using the training set, we're going to train some model. So we're going to minimize some kind of loss function that is defined over this training set. And then once the training is done, we're going to test our model on this held out set. And then that corresponds to minimizing an energy function that is defined by this trained model. All right, that often, we often refer to as the inference. And then finally, in order to check whether it actually worked or not, we're going to use the remaining test set in order to check the average evaluation loss. That doesn't necessarily have to be the training loss you use. So in the case of classification, we're going to use a 0-1 loss at the last stage. But until then, we're going to use, let's say, log loss or whatever the loss function that you want to use, like often the convex and differentiable. And then we're going to declare success if this evaluation loss is really, really low. And then we are going to say that, well, we haven't succeeded yet if the evaluation loss is not low enough. And then if it's not low enough, we're going to iterate the whole process. And then when it's low enough, when it's actually low enough for our kind of standard, we're going to write a paper. And that's been exactly what we've been doing. Not that great. So then, in order to go beyond asking for just a test accuracy, we need to go one step deeper. So instead of just thinking about, collecting data and then fitting a model on the collected data, we need to think about how we are actually defining a model, how we are defining various assumptions that are going to surround or on top of which we're going to build a learning algorithm. And then instead of just saying that we minimize a loss function, we need to think about how we are minimizing the loss function. What kind of optimization algorithms are we using? And also furthermore, we need to think a lot about how we do the model selection. That is, how are we actually finding the right hyperparameters? Often the hyperparameter selection is somehow hidden in a closet and then we never really look back. But that's actually one of the most important aspects of the machine learning. And that's what we actually teach in the Machine Learning 101. Except that everyone forgets about it immediately after the first lecture. And then the third thing that we need to think about is that how are these models actually solving the problem? It feels like these models are all complete black box, and then we have zero, let's say, sense of what is going on inside, but that's absolutely not true. That just means that we've been lazy. Things are happening. We can actually check exactly what is happening at the bit level inside these machines. And then it's actually up to us to figure out how these machines are solving the problem and then how that actually allows us to move forward. So I'm going to introduce, let's say, these three aspects of going beyond the test accuracy today. And then I just finished the slide deck yesterday, so it's possible that there will be some rough edges. I hope I ask for your understanding. And I'll try to go quickly so that I can cover all these three aspects today. So first, let's talk about, let's say, going backwards. So how does model solve a problem? So if you think about it, until recently, everyone was so focused on the classification problem where the answers tends to be one of the, 1,000, 10,000, 100,000 possible answers. Too simple. Now we are in our era where we are doing a structured prediction. And then here we have a bunch of people who are working on the audio synthesis, source separation, and so on, so you all understand. The space of the answers is in fact as large as the space of the input as well. And it's often combinatorial, which means that we can't really solve this problem exactly unless we get impossibly lucky or we make an assumption that make our lives easier rather than make the problem actually solved better. So instead, what we often do is that we're going to introduce a lower dimensional latent variable z inside our machine and then trying to solve the problem of the argmax that actually makes the problem somewhat more tractable. And then the interesting thing is that this z, which corresponds to, let's call it reasoning for now, although I don't really like that term myself, tells us how the inference or how the model has arrived at the answer y. Now, what does that mean? Is that if you have been following some of these, the recent advances in large-scale language models, you probably have heard of this let's think step by step, which actually is a pretty magical term. If you try with the ChatGPT or the OpenAI playground, it actually is a pretty amazing thing what it does. But what it does, what people refer to as a chain of thought does is that instead of trying to arrive at the answer directly, we're essentially doing an inference on both the internal mechanism or the latent variable z and the y that corresponds to a z. And then the nice thing is that now we can look at this z value, so that is that the steps of the reasoning or the thoughts that the language model does in order to tell whether the answer that the model has arrived makes sense or not. Sounds good. And then everyone says that that's true. So I decided to try it myself. So I went to the OpenAI playground, and then I literally just asked some of the questions, and then asked it to reason step by step. And then what you see is that well, it looks like the model is doing something correct. It's often correct for the correct reason, or sometimes it's incorrect, but at least the reasoning itself is consistent. So I can understand why it arrived at this incorrect answer. That's good. But then at the same time, you do see all those, the unreasonable, let's say, ways in which the models work as well. Sometimes it's correct for an incorrect reason. Sometimes it's incorrect for an incorrect reason. Sometimes it's incorrect by ignoring the correct reason for an incorrect reason. Can't really tell what's going on there. And indeed, this is something that I just tried it out yesterday. Like literally, I just opened up my browser, went to the OpenAI playground, and then I just played around a bit, and I could find this kind of examples very, very easily. And then indeed, it is not only me who has been interested in this one, right? So there are a bunch of work, for instance, from the Anthropic in California, and then some of the work from the NYU and Boston University on trying to check what it means for the Z to be the correct reason, and whether this chain of thought or how the language models are solving the problem indeed corresponds to a consistent or reasonable reasoning. So for instance, you can actually try to alter this chain of thoughts and then see if the answer that the model arrives at changes accordingly or not. Or you can also check just the literal correctness of this chain of thoughts as a proof. And then you can really see whether it works well or not. Overall answer so far is that okay, so these language models do something, but not quite as well as we want them to, or the people actually want us to believe that they do. And what does that mean? What it means is that there is some kind of, let's say, unfaithfulness that is embedded in this kind of models' ways to arrive at the answers. But then we need to ask questions as a scientist ourselves, what are kind of causes behind such unfaithful patterns of reasoning? And in order to do that, we need to think about what are the minimal set of the consistency that these language models must satisfy in order to even say that they can reason like humans in order to arrive at any kind of answers. So we're really trying to define this set of minimal consistencies and derive some test cases so that we can check whether these models, not even going into this kind of multiple steps of the consistency or the reasoning, we're going to see if these models are actually doing a single step of reasoning in a reasonable way. So a couple of the definitions and assumptions, these models are really, really complicated in the sense that we cannot actually do anything tractably. Learning is not tractable. Maximum likelihood with this kind of models is in fact NP-hard. Inference, so generation is also in fact not tractable. That's also NP-hard. In fact, that's an NP-complete problem. And then, so we're going to assume that we'll do some greedy approximation to decoding for generation. And then I'm going to use the term semantic equivalence here and there. And then if you ask me what semantic equivalence means, I won't be able to tell you, unfortunately. And then just trust me, and then let's say that if you think that the two things that have been said are same, then they are semantically equivalent. Let's just stick to that. That's the difficulty of working with the natural language. I'm pretty sure a similar thing with the audio as well as the music as well. And then I'm going to also define a replacement, which is again vague, but somewhat workable. So replacement is going to be to have some kind of placeholder in a language or the sentence, and then I'm going to plug something in to that placeholder. Now, why is it vague? Because language is not really strictly compositional in a sense that as soon as you replace some of the words, even with a word that is semantically equivalent, you often have to change the context to make it grammatically correct or make it syntactically correct. So what that means is that we can't really systematically define this kind of, let's say, replacement operator. But again, if it works in your head, let's just assume that it works. So what are some of the examples of the minimal consistency that people have already studied? Already in 2021, Elazar et al. Proposed something called self-consistency. If the questions were semantically equivalent, answers should be also semantically equivalent. Now, it turned out that almost no language model actually has this kind of consistency. So that's not a good start. And then more recently, Prescient et al. 2023, they actually proposed something called the equivalence consistency, or they didn't call it equivalence consistency, they called it like reversal curse, or the curse of the reverse, which is a horrible name. But what they are saying is that if I have two statements that are semantically equivalent, And then if I'm going to, if my language model says that the one of them is same as the other, then my language model should also say that the other one is same as the other one, the original one as well. So it's like the A equals B has to imply that the B equals A, which is in general not true in natural language. So it's a very narrow kind of, let's say, concept of the equivalence consistency. And then what they showed was that indeed these language models do not possess such equivalence consistency at all, not at all, I mean, to a very low degree only as well. So, I think my student, Angie, and some of the students at the NYU, we started to look at, okay, what are further, let's say, consistencies we can think of, these minimal ones? One is hypothetical consistency. You can actually forget about all these definitions. These are just written down in order for us to make sure that everything is clear. But the idea is that so we can come up with a hypothetical transformation. That is that I'm going to come up with a question, but then I can ask the language model, not only the question, but also a hypothetical transformation, or we call it identity transformation. That is that what would be the answer to this particular question? So I'm going to, for instance, ask you, how old was the president of Korea in 2018? But then my language model gives me an answer, that is that he was 65 years old back then. And I can ask the language model, what is your answer to the question, how old was the president of Korea in 2018? What we would expect is for the language model to answer the same way, 65 years old. But then, does it really happen? Not really. I again tried it yesterday. I just gave 2 examples, and then sometimes it does exactly what it should do. That is that it gives the same answer to all these identity, let's say, transformations. But more so than not, it's going to give you different answers. And then what this actually tells us is that, this language model really doesn't know what it's actually doing. Because if it knew what it was doing, it should be able to tell that it's asking about how this language model is going to answer the question, thereby the answer has to be exactly the same. And then another consistency that we decided to look at is a compositional consistency. This is even simpler. And then this really has to work for any kind of reasoning to work. What does that mean? Let's just go to the example. Now, on the left panel, what you see is that the language model is being amazing. What is a 4 factorial? It answers it perfectly, 24. And then on the mid panel, I asked a similar question, but this time a bit more complicated. What is a 4 plus 4 factorial? It gets the answer correct. But then I asked the same language model, what is a 4 plus 24? So 24 was the answer to the 4 factorial, according to this language model. But then the answer is suddenly incorrect and different from all the answer in the mid panel. And then this is really weird. Because what you can imagine is that what we want is that we want our language model to be consistent about composing the answers to the sub-questions in order to answer a bigger question. But apparently, these models are not able to do so. Again, this one, I just tried it yesterday. Right, this is the first example I tried, and then boom, it doesn't work. It's not really consistent in that way. So we came up with some of the protocol to check these consistencies, like hypothetical consistency. How are we going to do that? We have to come up with all these identity prompts. Right? So I predict that the next M words after this prompt would be answer choices, answer and all those things. And then these are essentially asking the language model whether it knows how it would have answered the original question had it been asked the question. So it's a bit convoluted, yes, I agree. And then what we do is that we had to come up with some way to check the equivalence, semantic equivalence of all these questions or the answers. But how do we check that, right? It's in our mind only, unfortunately, not in our computers. So what we did was that we made these questions and then asked the multiple different models for the answers. And then if these models actually know about themselves, they should be able to identify the answer that was generated by itself, but not by other models. And then that's how we make these kind of multiple choice questions that allows us to check the hypothetical consistency or the degree of the hypothetical consistency that is possessed by these language models. And I'll get to the answer. The answer is that these models absolutely have no idea what they are doing. So we try with all these different sizes of the models that are available via OpenAI API as well as the playground. And then what we see is that these models cannot actually tell what was the answer to the question that it already made earlier. And then it always is completely confused. What this really means is that one thing that we can actually say is that these language models do not really model their own reasoning process. and thereby cannot really simulate themselves internally. And then this really gives us a lot of thing to think about is that, okay, when we say these language models or these machine learning models are doing some complicated high-level reasoning, what does that mean? And then how is it possible for this kind of entities to have the kind of high-level capacity of reasoning without knowing what it's doing itself? It's an interesting question to think about. And in fact, of course, this protocol has a bit of an issue. Is that if the models gets really perfect, all of them gets perfect, every model is going to give the same answer. So this protocol cannot work. But fortunately, unlike OpenAI tells us, these language models are not far from being perfect. So this protocol still works, and then we know that these models don't really possess this hypothetical consistency. And then we can check the compositional consistency even more readily by using the arithmetic expressions. So we sample some nested arithmetic expressions, and then what we do is that we're going to take out all those sub-expressions, and then we ask the language model what the answer to these sub-expressions are. And then after that, we're going to combine them together in order to produce all these consistency checking, let's say prompts or the arithmetic equations, and then we ask the language model to answer that one as well. So the answer to the answer by the language models don't have to be correct, by the way, but they have to be consistent. The answer to the one in the center and then ones in the bottom have to be same. Because otherwise, what are we doing here, right? And then we're going to see how often that happens. Unfortunately, it turned out that except for a very large model, that is a GPT-4, almost no model actually exhibited this kind of, let's say, compositional consistency. And then what we see often is that more than 90% of these inconsistent cases are the cases where the models were all good. It was able to answer the sub-expression perfectly. It was able to answer the original expression perfectly. But then as soon as we replaced one of the sub-expressions with its own answer that was correct, it's going to get it incorrect. So there's a really weird thing going on. And then this, again, tells us that how the language models actually come up with the answers are not really about trying to solve the problem, but really doing a lot of the pattern matching and the stitching of the different things that it has seen during the training time, and then trying to give us the answer. And then what we see is that at least one good thing is that the more accurate models tends to be more compositionally consistent, which is a good sign. But at the same time, it just tells us that this kind of minimal consistencies may not be the valid protocol to check the reasoning capacity of these language models down the road, as the language models just see increasingly more data, and then becomes increasingly more accurate for the reason that is not the right reason that we think these language models should work for. So what we see is that despite their successes, these language models that have been trained to capture all these correlations in a large amount of data, it's not really consistent in a way that we want them to be. And then we came up with just the two minimal aspects of the consistency on top of the two that were proposed before, and then it's really not looking good yet. And then furthermore, what we are seeing is that as these models get accurate, it may look like these models become more consistent, but there is a very good chance and then the good evidence that it's not going to be for the right reason. So what do we mean by that? There was a paper that was just put online about 2-3 weeks ago while I was actually preparing this talk. That's not that great, right? So I had to quickly read this paper, and then this is from the MIT. And then what they show is that this GPT-4 is doing amazing at all these problems, like the arithmetics, the code execution, code generation, spatial reasoning, drawing, note in melody, even audio and the music related stuff, right? So it's amazing. So what they did, however, was that so let's start with the original data set in order to check how well these models do. And then they changed the questions in a way that is opposite, that the model should arrive at an opposite answer. And then this question would not show up in the training set, or is much less likely to show up generally. And then what you see is that the accuracies just dramatically dropped from these blue bars that are really close to 100 almost always, but then drops down to the almost chance level. What this tells us is that these models are really solving these problems really well because it captures all those amazing levels of the correlations that exist in the huge amount of data they use. But how they are solving the problem is not by actually figuring out the mechanism by which these problems should be solved. But then, I gotta say, they are super, extremely powerful and useful at the same time. So, it's a bit more like the research topic here, but it's something to keep in our mind on. So, of course, then question is, can we actually improve consistencies directly so that these models are going to have a better capacity to reason? I actually have no clue yet, but some of the keywords that I've been pondering upon quite a lot these days is making it more of an active machine learning. And then this is kind of closer to all those paradigm of the reinforcement learning from the human feedback and whatnot, is that you deploy it and then see what kind of feedback it gets and then trying to update the model on the fly. For a chatbot, it's fine, but sometimes there are applications where you don't want to simply deploy and see what happens. You can imagine a lot of them. And then the second aspect that I believe is going to be very powerful down the road is to make these models much more aware of the causality rather than correlation. Now, it'll have to be done from the observational data. This is not that trivial to do so, but these are some of the keywords that I've been thinking a lot about these days. By the way, before I move on to the second topic, big caveat is that the OpenAI really doesn't reveal much about the training models nor the deployment. So we don't know what kind of data they use, what kind of model they're using, what kind of, let's say, all those rules and then techniques that they have used for the deployment. So in fact, it's very possible that whatever I just told you is just an artifact of how OpenAI implemented things and never told us. And in fact, that's true for any paper that you read that relies on OpenAI's API and then run some experiments. I don't take any of those conclusions that seriously, including my own paper as well. Because who knows, it's possible that yeah, my own as well, yes. We all think that, when you talk to ChatGPT, you all feel like, oh, this is probably the answer that came out of the, collective knowledge of the humanity that is, collected in the internet. It's possible that you're just, listening to whatever Sam Altman wants you to listen to. So, always there's a big caveat here. But so, I hope, I was able to tell you that, okay, it turned out that just looking at the tested accuracy of the data that was just collected in the natural distribution is not really a good way for you to actually tell whether the model is doing or solving the problem in a way that you want the model to solve. So that was the first part. I'm going to move really, really quickly, but is there any question on the first part before I move on to the second part? Yes, please.
Yes, so one of these things when you're talking about taking a variation of the problem, you just flip that around and the answer changes. It sounds like if you're OpenAI and you have these background model-based things, you could generate these examples or augment the existing example pretty easily. So, you don't just feed in all the text on the internet into your language model and see what it does. You'd have to augment them and make adversaries. So is there something, we can only speculate, but in the balance of they're not using enough adversaries in their training, or the model is not, once it learns the raw data, it's not able to capture the adversaries and the augmentation data?
So absolutely, right? So how the OpenAI's models are so much better than most of the other models out there is because they've been deploying these systems, and then they've been receiving a lot of feedbacks on what are the things that these models are now working well, and then they can incorporate them. And then they're hiring a lot of people who are just creating all this further data to be used to train the next generations of their models. Now, unfortunately, that only goes so far. The reason why we are doing machine learning and so on is to solve a problem that we don't know how to solve, or we don't even know the answers to, like drug discovery and all those, or optimizing the healthcare and whatnot. There, we don't even know what is the right question to ask, and then what is the counterfactual to ask to start with. So that only goes so far, and then relying too much on the human feedback is thereby very problematic as well, in fact.
Thanks.
Yep.
I'm wondering, are humans are consistent? It's possible to construct such an experiment, like have, 20, 100 people and ask similar questions.
Yeah, absolutely. So are we as consistent, right? That's the question. We are definitely much more consistent in those minimal, let's say, stuffs than the language models. But then we are definitely not 100% consistent. And indeed, that's just because I think there are a lot of the irrational part of us. But yeah, absolutely. Not perfectly consistent. Humans are not perfectly consistent, but the language models tends to be more inconsistent than us, even on this kind of minimal stuff. But anyway, so that was how the model solved the problem once it's trained. But what happens during training time? So often when you go to, let's say, machine learning talks, what you hear is that, oh, here's our amazing loss function. Here's amazing, let's say, model architecture. And then we train it with the atom. And then here's the answer, right? But somehow what you realize is that in practice, the most amount of the time that you spend is on training. So you start training the model, you look at the loss function curve, and then you're thinking, oh, the loss is not going down. You reset, and then you try it again. And then if you're training, I don't know, like a 30 billion parameter model, then you have to wait for 6 months. And then you have to, who knows what's going to happen inside. But somehow we always kind of say that, well, here's a loss function, amazing network architecture, amazing data, boom, here's the answer. But then you have to, of course, at the end of the day, what is really carrying this whole field of deep learning, even now, is the optimization. So optimization should be the first-class citizen that we look into it really, really carefully. And then optimization really matters because at the end of the day, we're not really doing a training by exploring the entire space of the all possible models. That's not the case. The models that we're training nowadays have the billions, if not tens of billions, if not hundreds of billions parameters, but we never had that many examples. What that actually implies is that there's not enough constraints. If you just do the stochastic gradient descent or the gradient descent, you never actually fully explore the entire space, but it's going to be very low dimensional, some kind of manifold over which you're running the optimization or the learning. In other words, a learning trajectory is extremely, extremely localized, and we're only finding one solution out of many potentially equivalent solutions. And then this is evidenced by, let's say, many earlier observations, one of which that is most popular is this low trade ticket hypothesis. But then of course, you got to think about it. Okay, so then what kind of solutions are we finding if we run this kind of local optimization? We're definitely not finding all possible solutions. So then is there a way for us to actually characterize these solutions by looking at the optimization trajectories? And if you think about it, of course, these are neural nets, especially when it's over-parameterized, there are so many equivalent solutions. I can literally just permute the neurons or permute the attention heads, and then to permute all the other things accordingly so that I get the exactly same function. But there are going to be infinitely many of them in this parameter space. And then it turned out that there are many equivalent solutions according to the tested accuracy. So if you look at the left panel, on the top row, it says standard is all the accuracies measured over about 30 different models that were trained on the standard tested. And then they all get the 100% tested accuracy. It's a synthetic data, so that's absolutely possible. But if you look at the next 3 rows, what you see is that all these seemingly equivalent models according to the tested accuracy are very, very different. Some of the models are amazing at generalizing to, let's say, sequences of the repetitions. Some of the models are amazing at, the shorter sequences. But meanwhile, some of the models completely fail at the longer sequences than the ones that they were shown during training. So if we only look at the tested accuracies, we wouldn't be able to distinguish any of these solutions that we were able to find. But if you look at some of the other aspects of these models, we know that they are all different. And in fact, Garros et al. In 2020 draw this, let's say, nice kind of diagram that shows that, okay, there are so many different types of solutions, and then we can try to, they put them into a different levels or the different let's say, families of the solutions. So how do we actually know? How do we know? In fact, what we do is that already from 2018 or so, what natural language processing as well as computer vision community has been doing is to come up with so-called challenge sets. So we're going to come up with a specialized test set that's going to measure particular aspects of the trained model. And then in fact, this was done by the, Tal Linzen, who is a professor at Center for Data Science at NYU as well. And then what we do is that, okay, for this particular aspect, this model is better than that model. And then we're going to say that, well, the model that does better is more robust along that line. But of course, this is great only if we know what to measure. But we never know. We almost never know what are the right aspects over which our model should be more robust to, more sensitive to, and whatnot. We never know. We get lucky in natural language once in a while. We get lucky in computer vision once in a while. But we almost never get lucky anywhere else. So then we need to think about what other signals can we use in order to figure out these kind of, let's say, various aspects of the final solutions. And then optimization trajectory turned out to be one of the great way for us to pick up on all these, let's say, hints. Because the learning is not really a homogeneous phenomenon. The choices of the hyperparameters and the stochasticity drive learning. And then these are the big things that we kind of, let's say, ignore quite often, unfortunately. Furthermore, learning is not a monotonic phenomenon as well. So what happens is optimization progresses in multiple phases. That's what people say, but I still have my doubt there. But then at least what we see is that there is some kind of, let's say, different time frame within learning where we can see that, oh, something weird is happening. So for instance, what you see is that you probably heard of the term grokking, which I think is the horrible way to actually describe what they described. But anyway, the idea is that when you look at the training loss and then when you look at the validation loss, their relationships are not really monotonic. They change over training runs. So for instance, if you look at the left panel, that's a paper from 2016 based on the work that was done in 2013 by the Chalar Gulser and Yasha Benjam. There is a early stage, the validation loss just never drops, although the training loss dropped really rapidly. But over time, training loss starts to fluctuate and then drops. But this drop is preceded by the drop by, followed by the drop in the validation loss. But there's always a gap. But the gap is not really homogeneous. We can't really easily characterize this. So then now the goal is to actually pick up these breadcrumbs along optimization trajectories and then trying to see how we can, if we can tell based on these breadcrumbs, whether the final models are desirable or not. And in fact, some of my earlier work from 2019 showed that one of the breadcrumbs would be, okay, so let's see how, at the spread all these stochastic gradients are. If they are more spread, it seems like, it leads to a better generalization. So, there are all those breadcrumbs. But then the question is, how do we actually pick up those breadcrumbs? What everyone is doing at the moment is that they look at the loss curves really, really carefully, and then think a lot about what it means to train these neural nets, and then make some hypothesis and test it. And the hypothesis tends to be really simple. Something like, it's going to be the covariance of the stochastic gradient that I need to check because that is going to tell me how the generalization is going to happen. But then if you think about it, that's too easy, right? If there's a one number that tells me whether the model is going to generalize perfectly or not, why are we actually training these 30 billion parameter models? There's apparently a one number that actually tells us everything. So it's actually a really difficult problem. So what we decided to do, and then it turned out that it's a great way to go about it, is that we use machine learning to analyze the machine learning algorithms. So what we did was that, here, it's an audio crowd, so you all know the HMM, right? So great. So, because, we don't teach HMM anymore at university, so sometimes it's a bit frustrating. So what we did was that we actually extracted out a number of the features from these models that are being trained over time, and then we fitted the HMM on top of this in order to identify or discover this hidden state underlying this process of optimization. And then some of the features that we use, we could use the entire parameters, of course, but we know that it's anyway very low dimensional phenomena that learning is happening, and also fitting a HMM on a 7 billion dimensional space is kind of, let's say, tricky. So we decided to choose about, let's say, 20 or so, let's say, features. And then what HMM gives us are twofold. One is a transition matrix that tells me how the phases actually evolves over training. And then second one is the emission distribution that tells me about for each of the transition, what are the important features of this neural net. And then by analyzing these two things, transition matrix and emission distribution, we can now pick up all these breadcrumbs automatically and systematically. We're not going to decide which feature is important. That's too, like the pre-machine learning or the pre-data science, right? So, we have all these amazing machine learning tools, so we're going to use them. So here's an example. So we trained the ResNet 18 without batch normalization nor the residual connection, I'll tell you why, on CFAR 100. And then we trained it many times, and then we fitted the HMM. And what we see is that there are actually two different paths in this HMM state space via which learning can happen. And then one of them is better than the other. And then we can actually identify some of the states that are undesirable in terms of the convergence as well as the generalization. And we can do the similar thing. So I mentioned about the grokking. So we wanted to see, whether that kind of grokking that is that the training loss goes to 0, but the validation loss doesn't go to 0 until very long time. So we decided to try it on the one-layer transformer on modular addition. That's the kind of standard thing that everyone does, which turned out to be actually very incorrect. And then we can indeed identify the state that corresponds to this phase of the grokking phase. That is that the training loss is going down, went down, but the validation loss is actually not going down at all. And then these are all kind of automatically coming up. And then the paper is online and then under review at the moment. And then you can actually take a look at it. And what you see is that you can find what are the features that drive this kind of, let's say, transition, either desirable or undesirable. And then that really gives us a sense of, okay, what are the things that are really important? And then using this, we can now put one more machine learning algorithm, linear regression on top, to automatically identify which states are desirable and which states are undesirable. And then we can define something like the detour state. Whenever the learning algorithm goes to the detour state, this is not going to end well, kind of thing. And then we can do that automatically. And then, but then the one thing this is some kind of byproduct that we found is that in fact, it turned out that the whole deep learning community has been doing something really, really well. We introduced a residual connection. We introduced all those normalization layers. And then as soon as we add those batch normalization residual layers, all those bad states disappear. So the one on the bottom is the one that I showed you earlier, ResNet18 trained on CFR 100, after removing the batch normalization residual connection. But if you do the same thing with the original ResNet18, no detour state exists anymore. So it's just one, let's say, nice chain that every learning goes through all these states, and then the answers are almost always good. And interesting thing, grokking disappears as well. So in grokking, if you follow the Nanda et al. 2023 paper, what they do is that they actually didn't have the layer normalization, and they used a really large batch size, and then demonstrated that all those the grokking happens. It turned out if you add back the layer normalization, and then decrease the batch size to increase the stochasticity, and then do the same analysis, all those undesirable detour states disappear. It's just a linear chain. That's about it. So what really tells us is that these are all kind of confirmation of how we can do this kind of analysis using machine learning ourselves. And then what this really tells us is that we have to learn to use machine learning algorithms, not only to solve the problems that we want to solve, but also to analyze the machine learning algorithms that we have designed to solve the problems that we want to solve. So it's like the machine learning all the way down or up, right? So what are some of the next steps? So the second bullet point is the one that I really want to focus is that what we have seen is just like what we talked about earlier, is about correlation. So by looking at all those training trajectories, what are the correlations that exist between the features and the transitions of these hidden states? But can we actually establish some kind of causal relationship between modal quantities, so those feature values and the states? Because if we can do it, then we'll be able to intervene as well, so as to avoid going into those the bad detour states, or make the learning algorithm escape those detour states that it got stuck at. And furthermore, what we want is that we take one step further and then fit one such model that analyzes all the training trajectories coming from all the different models as well as all the different problems as well. So then can we actually come up with this kind of, let's say, meta setup where we'll be able to come up with some small number of the intervention rules to make the learning more generalized better. So here, the second part was about optimization trajectories, super interesting. But we cannot look at it. We are very bad at looking at anything that is over 4 dimensions. So we have to use machine learning to analyze machine learning algorithms. So Juan, I guess I've run out of time. Yeah. Okay, so then I'm going to just wrap it up. The third part is slightly less, exciting. I love it, but it's boring to majority of people. So I'm going to skip that one. But I'm going to just wrap up by saying that, it turned out that Leon in 2015 was absolutely correct. When we look at the tested accuracies, in particular, assuming that every examples was drawn from the identical distributions during the training and test time, doesn't really get us too far. And then in reality, world is changing nonstop, and then things that we want our model to learn is to be able to adapt or they learn to be invariant to the changes in the world. And then to do that, we have to go beyond just checking the tested accuracies. And then there are so many skeletons that we've been hiding inside the closet. We talked about the optimization, we talked about the inference, and the third thing I didn't talk about was the actual assumption behind our machine learning algorithms. And then we really need to kind of revisit every single one of them to make sure that we haven't forgot to pick up on some of the breadcrumbs that have been left all along. And that actually concludes my talk. Thank you.
Many thanks for the excellent talk. Questions from the audience?
my talk tends to be very clear, so nothing left for questions, right? Yes. So then I'll be around, so yeah, you can talk to me. Oh,
So I have one question about the optimization dynamics. I wonder, they change a lot based on how big the model is and how many how big the data set is, and how do you think those two things kind of play into
yeah,
that?
absolutely. So so we in our case we actually did the analysis of the optimization trajectory per model, per data, and per task. But then I think that what is actually going to be really interesting is whether we can come up with this kind of analysis method that works for the multiple setups. They are not necessarily homogeneous, right? So the data set sizes may vary and so on. And of course, every time we change something, this optimization the dynamics changes. And then this is exactly what you're seeing is that the hyperparameter choice is going to change how the optimization happens. And then the hyperparameter, of course, includes the size of the model, size of the data set, and so on. So yeah, that's absolutely the natural next steps to think about. Yes.
I have one, but you want to go? Something that caught my attention is you said that we can potentially analyze every bit of these models. What's the roadmap to get there?
Okay. So,
or is it worth it?
yeah, I did say that what I meant was that not even hypothetically, in practice, we can actually check every single computation that is happening, right, in any of these black box neural networks. But those tends to be extremely high dimensional. And then one thing we don't know how to do well is how to look at the high dimensional data and then get the sense out of it. But then one thing we have figured out over time is that we can build an algorithm to do the understanding for us or the analysis for us. So this is one of the examples. In fact, if you think about the optimization trajectory, there's one trajectory in about, I don't know, billion dimensional space. We can look at it and then make sense of it. But we can now build our machine learning algorithm so that it's going to make the sense out of it and tell us what to look into. So in a sense that we need to do the dimensionality reduction, and then we're not going to do it by looking at all those bits ourselves. We're going to do it by asking machine learning algorithms to do it for us.
I guess I have two questions. The first one is brief. On all that language modeling stuff you were talking about earlier, you were using things that use a sampling strategy other than argmax. Is that right?
Yep.
So given that you've got I'm trying to understand why you would ever expect consistency from something that samples randomly at every step. So why was that a question?
Okay, that's the first question.
That's the first question. And then the other one was, in your, hey, I can see that I'm in different parts of the learning trajectory. Is the goal of that so that you can stop training because I say, I'm in a bad part of the trajectory and I expect that I'll never get any better? I was trying to understand once I've understood that there are different states that I could be in, what do I do with that?
Yep, that's a great question. Okay, so the first one first is that unfortunately we cannot do the exact decoding with these language models because they don't have any of the properties that we can exploit to build the exact decoding algorithm. They are not Markovian, and then they are nonlinear, so we cannot use any of the techniques that we have built for various, let's say, state space models and whatnot. So it's become very much at the standard to just use a greedy decoding or a bit of a stochastic sampling. Now, indeed, stochastic sampling or the greedy decoding, these inexact, let's say, decoding algorithms may be the reason why these models are not showing us that it's doing a consistent reasoning. But then the question is, if we don't have an option other than, let's say, greedy decoding or whatnot, then what does it mean for the model to actually be consistent internally? Just that we don't know how to get out of it. So that's the one thing. But of course, people are working on the decoding algorithms. That's actually, that was my major kind of, let's say, research program over about 5 years, until about 2 years ago. It's a difficult problem, but you're perfectly right. There are so many moving pieces, so we have to be a bit careful in drawing a conclusion, in particular because we don't know what OpenAI does. So OpenAI says that if you use these parameters, it's going to be greedy decoding. So that's why we're using it. And we say, oh, we trust them. Well, who knows what they're doing? I mean, the weird thing is that every time you run it, even with the almost same amount of, let's say, tokens that you give, the outcome, the return, latency is different. And then you have to wonder, why is the latency different when the computation complexity should be exactly same every time? So we don't know that. So that's the answer to the first question. The second question, the overall goal of this kind of analysis of the optimization trajectory, some people just do it because they think it's fun. Actually, my former postdoc Naomi, who actually led the whole project, who is now in Harvard, she told me that she just finds it really fun. I was like, okay, that's great. But I'm more of a problem solver. And then the reason is, I think, number two, is not to just stop training, but more like, can we figure out an interventional strategy in order to avoid those the undesirable states? So that it's not going to be just, oh, okay, so training is not going well, let's stop. But more like, oh, training may not be going well, so can I actually intervene in the training process in order to make sure that it always goes into a good place?
All right, let's thank our speaker once again.
Thank you.
Yes.